Yeah, so my name is Anna. I'm a research fellow at the Alan Turing Institute, and I've been working with the Heigit and Heigit. This research was carried out with Marta and Benny from Heigit. Yeah, I'm going to show you what we found out on how fAIr works. So starting from that, this is a GIF file I got from this website, from Heigit, and it just shows you the ending point. So what it does now is try to run a prediction on buildings for a model which has been trained locally. And what fAIr provides is some pre-trained model, and you can basically retrain locally from. So I'm going to more specifically on how this works, but this is basically the ending point. And this GIF shows you how fast it can run the prediction. So, but actually, what you see online, what you actually act on as a user, as an OSM user, is this part, the labels and the prediction. Whatever is in the middle, you don't really see, you don't touch, you don't need to know it, you don't need to understand the AI or anything. fAIr does it for you. But I want, as a researcher, to show you what actually happens behind. And so just a brief introduction. So the labels come from OSM. So it's vectorial data, which you need to convert to a raster. Eventually, it's a binary mask. So it's either buildings or no buildings, 0, 1. And this is together with the ground truth data, goes into the machine learning process where training validation happened. Some checkpoints, they're called here, they are saved, so the weights of the models, which are locals for each of the areas that you want to train. And then you can run prediction on that specific area for the image that you have trained. So as researchers, we want to concentrate more on this part. And some research has been done already. I presented at Nairobi a research on the accuracy, on the performance of fAIr for a specific model at the time. And this is what I'm showing to the right is Radim from the Masaryk University in Brno. And he has spoken in Manila, and he was showing the difference. I research that I've done on comparing the performance of manual mapping versus the fAIr mapping, which I think is very interesting. I'm not going to add that into the results, just look for the talks when it comes out. So in this specific piece of research, I'm comparing the two models. They call them models, but models is very much used in everything, but it's basically the backbone structure of the machine learning, which is at the base of the machine learning. And initially, for fAIr, they used RAMP, which stands for Replicable AI for Microplanning. It was developed by WHO, specifically for the Global South. And lately, YOLO has been introduced, which is you only look once, and it's a very much used model in computer vision problems. So for this, to study this comparison, I have used the same data set which I used for RAMP initially, which is, I'm going to show a map, but it's 25 urban regions or cities spread around 21 countries around the world. It is at 3 different room levels, so 19, 20, 21. The total images which I've used, then separated by cities, is 8,400, and there are tiles of 256 by 256. So this is the distribution of the data sets. I've tried to cover as many areas as possible around the world, depending on the availability of RGB images. And I tried to cover different categories. So I've classified within different categories to be able to cover more, as much varied possibilities, like of buildings. I haven't mentioned so far, like what fAIr does, it detects buildings, right? And ideally, they would want them to extend it to other type of features, but at the moment, it does buildings. So, okay, I'll consider 3 different categories. Level of urbanity, so we have rural, peri-urban, urban, and refugee camp, which I consider a different class. Then roof cover types, so I found 4 different classes, which are shingles, metal, in general is thin cover, cement, and the mix where it didn't enter in any of the other subjects. And this is the category which I found was more interesting for RAMP, and which was affecting the results. So by density, I've classified dense areas, sparse areas. And the grid is something in between, where sometimes it's also sparse, sometimes it's more dense, but in general you have a pattern or a recurrent direction of buildings. And ideally, what we found out for fAIr is like sparse and grid area performed better than dense areas, which was not obvious, but that's what came out. So, going to compare RAMP versus YOLO, we go back to the workflow I was showing you before. And basically what we've done with this research, we set a workflow for comparing different type of models, not necessarily only RAMP and YOLO, but other type of models which can be introduced inside fAIR. So the step 0 is to create data sets for the two models which are the same. So basically, we need to separate the data between the trained data, validation data, and test data. And this is not so straightforward to do for the two models at the same in the same way, because they ingest different type of data. So RAMP wants GeoJSON and GeoTIFF for labels and rasters, while YOLO wants PNG and TXT. So you have to convert them and to have them to pre-process, and it's a whole thing just to solve this initially. Then the step 1 is what we did. We run a cross-validation on 5 folds. So what we did, we put the, you don't really see, it's a bit, it's very faint. The test data which we have, we put it on the side. We take only the training and validation data. We separate that in 5 folds, which means that each of the data is taken at least once. We repeat the process 5 times, so each of the data runs once as a validation data. And the model, and we do this to check that the model is not biased, like the data is not biased, and then therefore the model. Okay, so we run these 5 times, 5 different epochs, which is epochs is 1 run of the model. So I've done that for the 2 models. And then on this, we could run metrics, which are actually run during the validation process. And then we could test, compare the accuracy and the performance here. And then in the end, we run again the training on the test data, which was put aside before. With the test data, we can run the prediction and visually try to compare how the 2 models perform. So that's the framework which I've created to run this research. So first step, the folding. This is just to go through very fast, but basically we show statistically that in both models, while for this is the accuracy, I took the average for all the epochs and for both models, and we see that the data is much more spread for YOLO and is less spread for RAMP. But in general, these are the 5 folds. And but in general, we see there is accordance between the data, and so we consider it is not biased. And then, I talked about the metrics before. So these are metrics which are generally used in computer vision tasks. RAMP and YOLO have a default metric which is different, so I couldn't compare them on that metrics, but that's what the model gives you in output as default. And I've chosen these 4 metrics, which basically you can find in this good library. Initially I wanted to suggest a bad metric, but these people did a great job, and what they suggest to use this IOU. So IOU is an intersection of a union, and it tells by itself what it is the ratio between the intersection and the union of the real data and what you would want to see and what is actually predicted. And while precision, recall, and F1 score are given by this type of diagram, where you have what should have been predicted, the prediction, and precision is what actually was supposed to be predicted right, so the true positive, is the ratio between this and the actual prediction. And the recall is what has been predicted and right on what should have been predicted right, okay? And the F1 score is an harmonic mean of the 2. So in general, it's a value in between. Okay, this is the most complicated slide. I tried to make it simple, but this is to show for each of the city, I have 1 value of the average of the metrics for each of the metric. And basically what you would like, ideally, if both of them work well, they are on the 1-1 diagonal here. They perform 1, like 100% both of them. And anything below that means that the model is not performing great. So, but the values of ramp, they are all aligned around 0.8, 0.9. You see, you can, especially for IOU, while YOLO has values that range from 0.4 to 0.8. So in general, what we see is that all the points are above the diagonal when, let's say, so basically ramp performs always better in average. And ideally, let's say if both ramp and YOLO were performing not so great in this city, it would be here. And all of them, let's say one city doesn't perform well in both models, all of the city would be on the diagonal, right? But in general, what we see is that ramp performs better than YOLO. So I thought it could be interesting to compare, like the third step, the places where, cities like that, where ramp performs and YOLO performs bad, cities on the opposite corner where both performs good, and places where in general ramp performs quite well and the YOLO performs worse, and try to see why, and if we can understand why that happens. So I'm showing you here. This is a city. It's not really a city. It's a refugee camp in Kenya, and both ramp and YOLO are supposed to perform well. So what I show you is the RGB image, the labels, which are the binary mask I was telling you before. On top of this is the prediction of ramp, and this is the prediction for YOLO. And the red one, which you don't really see much, I think, for the lights, is the polygonization of the labels. So the difference that you see is what is wrong, basically, right? So this is an area where both of them performs well. And in fact, you can see relatively good results. This is one of the best results we could see. But yeah, the houses are basically squares. The background is very dark, so we expect them to work well, and they manage. This is at different zoom levels, so 19, 20, 21. And we see that at a higher level, there is some artifacts here. Both of them here, for example, don't manage to predict this building, which probably, I don't know, it's a darker building, so maybe the models didn't see that very much. They mainly see white buildings, right? So here is the first example where we see that the labels make a difference. So if I want the model to learn dark buildings, I need to teach him to show him dark buildings. So this is another dense area where both are supposed to work well. And also, again, they miss this building. And these are round huts, which are not seen. Probably they haven't seen them at all, so they don't see them, also in the prediction. So this is an area in Montevideo, in Uruguay. It's a grid area because you see it's dense, but it has a patterns of orientation. That's what I was telling you about before. So what I'm showing here is that the building is the models are instructed on cement buildings. And in fact, ramp here doesn't work well, YOLO works better. But in fact here, what maybe I would have drawn as buildings, they don't find them because here they're not being instructed to learn those, right? These light blue cover buildings. You don't really see well in the images, but there is quite much of a difference between these data. And in fact, it works at different zoom levels. It works quite well. This is the same building at more zoomed in and zoomed out. That's another area where they agree in not being working well, which is weird. This is a sparse area in Croatia. And it seems to work relatively fine here, right? But here, for example, they don't see this building at all. It's not clear why. And from the developers of fAIr, they suggested it's possible that when it's a sparse area, actually the model is more confused because you see more tiles without buildings. I'm not really sure that that's the case, but because there are areas which are very dense where also there are tiles with no buildings at all, but I don't know. I don't really know. It still has to be investigated, this behavior for this area, which is sparse. That's another area of Montevideo, which is very dense. Both of them performs bad, like in terms of metrics, and they do also visually. You can see, well, that's super hard, but a general thing that we see is that when it's hard for a human being to map, it's also hard for the computer. This is interesting, I think. Both of them work bad for IOU recall, but precision does very well. What is interesting here for me is that I managed to see these as buildings when it could be also a courtyard, right? It's just I've mapped them myself, the labels, so I know that it's really high tall buildings. And it's interesting here that the ramp manages to see beyond the trees. And while YOLO is very much confused by the trees, you can see here, especially. And that's the same here. YOLO is very much confused by the trees. We will see again in other parts of in other labels. But here, somehow, it's really hard to map them, and they kind of did a good job, honestly. Yeah, this is a place where in Dhaka, where they both not perform well. Here, again, this is a grid area in Denver, in the US. And again, ramp can see beyond the trees, and YOLO doesn't. Well, it doesn't see much. But yeah, in fact, the image is not really clear itself, right? So maybe that's why they both not perform good. That's a sparse area where they're kind of average, both of them, and this is in New Zealand. And they work kind of well, both of them. Maybe ramp a bit better here than YOLO. That's another sparse area where ramp works much better than YOLO, though visually the results are very similar. YOLO tends to overestimate buildings here and here. And what we have here is that both of them, I mean, ramp is only fooled once from the trucks, and YOLO sees many houses when there are trucks and other stuff here on the bottom right. Another areas, this is in Pemba in Tanzania. Both of them actually see a building where the labels didn't have it. And it's probably, I would have mapped it as well. So the question is maybe the labels were wrong. And this happens here as well. These are two small buildings, though that are not detected. Maybe that's a matter of size. So what I'm trying to show you is that the labeling that you do is very important, apparently, because the model learns what you tell it to learn. That's another area where ramp performs better than YOLO. And we see, again, YOLO kind of overestimates buildings when they're not there. Yeah, and here, I'm showing this because I think that's a relevant case for like zoom levels. So in this image, it would be difficult without other context to understand if one is a building or is a road or footpath, whatever it is. It's all kind of similar cement type of cover. And though both of them managed to kind of, YOLO has some artifacts here, but ramp is doing a decent job, I think. That's another sparse area which is in Russia, where the zoom level also makes a difference. So basically, depending on the context, if it is a rural village in Africa or it's a big blocks area like this in Russia, blocks can take up, you can see a whole tile just covered with cement. So it's really important, again, what you give to the model to learn. So in conclusion, how does this model perform? Is it a yes or a no? I think in between all of this, there is all the consideration that you have done. So if you want to use fAIr, you want to train it, you be careful of the type of labels that you use. Okay, be considerate of the zoom levels that can be used for that type of area. Again, we're saying sparse, not sparse, dense. And I think what matters as well is the polygonization, because what you get in the results is those polygons, but actually the results is rasters. So how is it polygonized? Which is something you can actually tweak also in fAIr. And comparing the two models, so in terms of metrics, ramp wins. In terms of being able to identify buildings beyond the trees, also again, ramp performs much better. Though YOLO is much faster, and that's one of the reasons why it was deployed, is like twice or even 3 times faster to run. So depends where you want to use it, but if you want something super fast, the better to use YOLO. So I leave you with this question, like this is the best performing, easiest model possible. Its grid is aligned north-south. The houses are all the same. And these are the results, okay? So it's, of course, a provocative question. Would you use this to map in OSM? Or maybe, I mean, a possible situation where I would try to use this type of results is I need just to know where the buildings are, more or less, just to give an idea for a disaster situation. And maybe this could be used for that. Could be used for OSM. I don't know, maybe it's faster for me to map the 6 corners here rather than run the whole training and have the results and then go through the validation process, also from the feedback from the users and so on. So yeah, that's my contacts if you need. We have the research on, everything is on GitLab. That's a website for HOT. And yeah, I'm happy to start any conversation on this. Thank you.
When it comes out of the models, is there like do they do a post-processing to make them proper squared off buildings?
Let's go to the first slide. I didn't go.
I think my general frustration is I'm expecting it to, it's getting all the labels are very square, and then I'm getting a raster.
No, so yeah.
And I'm like, why doesn't it know that buildings are square?
The results is a vectorial. I was just showing you the results of the model internally. Yeah. The results is vectorial, and it's a polygonization of that raster. So yeah, you can say, depending on how I tweak the polygonization, I can get different corners, right?
Okay. Yes.
What it does at the moment produces this type of results. And when you run it, you can yourself decide, it's going to show you in a second. You can decide whether you accept or not the results. Yeah. Whatever you accept, you can download as a JSON, as a file, and run it at home on JSON, for example. You can import it on JSON and then decide to map it yourself, or just do what you don't. Or you can also import it send it to OSM. Or what it does, whenever you click a yes or no here, like accept, or what's the other option, like it goes back to HOT. At the moment, they do nothing with that, and there is the option, they're speaking about integrating it with the map swipe. That's what Nico was speaking about yesterday, to send this output as data for validation in map.
The polygonization bit, has someone actually written code to generate that?
Yeah, it's here. Actually, what it does, it gives you only the polygonization. You don't see anything else. What I will show you, I'm running locally. And here you have a tolerance and an area.
Some of those buildings are it's got too many lines.
Of course, yeah.
I would adjust the code to make it fewer lines.
So do you see this bit? They allow you to tweak that. So you can run the, so the tolerance is a matter of how many corner sites you're happy to tolerate, and the area is like anything which is below this area, just eliminate it. And that's the confidence level as well for the prediction. You can change. So you can tweak a bit and then see how the results change with that. Some of them are good, some of them are much less. Yeah?
Given the tendency of some people to try and use AI to do all their hard work for them, what are your limitations on imagery resolution and of nadir?
Okay, so in general, the model works well with the resolution is asymmetric. And the images come from OpenAreaMap. I didn't show that. It's another service from HOT where you can upload, in general, drone imagery, like unmanned air vehicles stuff. So you can upload your image and then import it to here as well. I wouldn't know. But at the moment, you see, when you run the prediction, it generates for that area only. Yeah. They were showing.
The imagery that we get to use is nothing like as good as that.
Yeah. But you can actually explore what there is in OpenAreaMap. There's a lot of data there.
Available.
When you say we, what do you refer to?
Too hot.
Okay. Other questions? Sorry.
Thanks for this slide on the metrics and how this graphically represents. I really like that. So you talked about context and contextual, differences in there.
Yeah.
Did you see any specific, geographic contextual elements in there? So certain alignments in buildings for certain regions of the country, predominance of certain surface materials that you can probably signal. Perhaps the model can work, probably not at the global scale, but probably some regions that are performing better than others.
No, I would have hoped. That's why I did, as I showed, the different categories and tried also that the categorization is very personal, very subjective. Like, you know, yeah, more this. This could be even considered dense in other parts of the city, right? So I couldn't find anything. It's super difficult to try to categorize that. I've had people approach me to say, can you help me to find the roof covers type? And in the same cities, like I zoom in an area which is homogeneous, but it changes so much. And you can have, this could be as well be in Europe or somewhere else, right? And the same. I mean, this is a refugee camp, so it has specific connotation, but there are things which repeat around the word and are not really specific for each region, when I thought there might be more differences, and I couldn't find it. Yeah. Yeah?
Thanks very much. I guess I'm just thinking about what the results tell you about the fundamental algorithmic differences between the two models.
Yeah.
So they are different models, but how are they different and how are they composed? They're taking the same data, they're producing different results, which implies there's something different in the way in which they're processing the data. So what is that difference?
The difference between the models?
Yeah.
Okay. I didn't go deep, but so they're called convolutional network, neural network models. And what they do is basically, there is not much more than 4 or 5 type of techniques that they use, which is like filtering, is like working on matrices eventually, and they do filtering or other type of like image processing stuff and tasks, and they are repeated in different ways basically. But what you get is a tree of different operations that the images go through, and what changes between them in the end as a structure is the number of time one operation is repeated versus another one. But more or less they do all, I would say, the same stuff. But some more machine learning people, as expert people here would maybe contradict me, but that's my understanding. So they differ in the order in which they do the operations and how they handle the data. Like, because the data is complex in three bands and is you know, goes through the washing machine and something happens out of that. Okay.
Maybe have time for one more quick question.
Okay. It's okay.
Thank you very much.
Yeah, thank you. Welcome.